Just as a Formula One champion pushes their car to the limits, AI workloads must rise to the challenge of relentless scale and speed. Dense fog can impair a driver's vision and cause them to slow down. Lack of fine-grained visibility down to the Q-pair level causes AI teams to slow down, whether at GPU cluster onboarding during pre-race time or at race time for their workloads at runtime. Debris on a track can cause crashes. Similarly, NIC and link flapping causes AI workloads to crash and costly rollbacks as early as within the first hour of a GPU cluster. I'm Lerna. I'm a solutions engineer at Clockwork, where I help customers achieve their performance goals with software solutions built on our foundational research. Before this, I was at AWS for 3 years as a solutions architect. And before that, I was an infrastructure engineer for 17 years in large financial services companies, where I worked on centralized authentication systems, distributed caching for an investment management portal, and low latency monitoring application for all servers in the firm, the downtime of which would have impacted trading applications. So I enjoyed this type of problems of scale that require solutions that are highly scalable, available, and resilient. And in this session, I will cover AI/ML networking challenges with demos that touch upon learnings from a solution that provides Q-pair level visibility to pinpoint root cause of issues quickly when it comes to connectivity, and automatic recovery from NIC flapping to prevent crashes, so that we get the visibility and reliability that we need to keep our AI workloads running at full speed, like a Formula One champion's car. First, we're going to start with AI workload layers. On top, we have an LLM model. It is using libraries and frameworks such as DeepSpeed and PyTorch for optimization and deep learning in this case. If you have a large-scale job, then you need inter-GPU communication. So you use collective operations for this. And for that, you use libraries like Nickel, which is a collective communications library from NVIDIA. At the bottom, you have the network card that needs to be able to speak over InfiniBand or RoCE and has to be RDMA capable. RDMA is a key feature that enables fast data transfers going from one node to a remote node's memory over the fabric, bypassing the kernel. And these fabrics, they provide us high throughput and low latency. The top two ones that is used as RoCE v2 and InfiniBand, they differ at network and link layers. InfiniBand relies on proprietary protocols such as these two and requires proprietary hardware. It performs really well, but it can get costly due to this requirement. On the other hand, RoCE v2, it relies on standard protocols, UDP/IP and Ethernet, and requires standard hardware. So it performs comparably well, and it is less costly. So what are the demands of these AI workloads from their networks? Traditional networks, to me, they are like busy streets in a big city. And AI networks, on the other hand, are like high-speed racetracks. So traditional networks, you have delays because of packet drops and retransmissions, and you expect best effort service. In AI networks, these networks are designed for lossless transmissions, so you expect minimal delays and you get best performance. Operating link rates, they can go to 25 gigabits per second in traditional networks, and you get 50% or below safe link utilization, so you don't have too much congestion. AI networks can go anywhere from 100 to 800 gigabits per second and 95% or more safe link utilization. So these workloads are running all the time, so that's why the link utilization is quite high. In traditional networks, you have heterogeneous workloads, elephant and mice flows when it comes to throughput, and the speed of one application doesn't directly affect the speed of another app. AI networks, on the other hand, you have homogeneous workloads that are highly correlated. So let's dive a bit deeper into those. So if you were to profile an LLM training job, you would see that it consists of cycles of compute followed by communicate for each and every iteration. And if you look at the overall job completion time, 30% or more of that is spent on networking. So let's take a look at all reduced collective. So here the components of the sum, they're getting passed around the ring, and the total sum is computed, And then that total sum needs to get passed around the ring again, so each and every worker node has the total sum. So the finish time of this operation is based on the sum of the latencies in this rank. So just like at a pit stop, a pit crew is not done until all teammates are done. GPUs are not going to proceed to the next step until all GPUs synchronize their partial results, like partial gradients, for example. The slowest team member in a pit crew is going to determine the speed of the team, and the slowest flow or node is going to determine the job throughput in the case of AI workloads. So if you look at the collective communications library, here I have two nodes, 8 GPUs each and 16 network cards. GPUs, they are generating messages that get split into chunks, that get mapped to queue pairs. And these queue pairs, we can think of them like sockets. The network cards are taking this data, packetizing it over the fabric, InfiniBand or Rocky, and then the receiving network card is taking it up its stack. The interconnection fabric is either a FAT3 network or a rail-optimized topology. So you always have the top of rack switches, and then on top, you can also have spine layer switches and core layer switches. So if you look at the challenges within AI networks, especially this is what we hear in the field from GPU cloud operators and their customers, these are the issues that we see today: lack of visibility, lack of reliability, and lack of predictable performance. The first challenge is lack of visibility. And here's an alert that one of these teams received. Top of rack switch has 3 down uplinks since 6 months ago, but they're not sure why. This is happening because these teams are lacking real-time insights when it comes to connectivity between the nodes, quality of these paths. They only have aggregate level metrics, but they don't have any fine-grained instrumentation. They specifically don't have visibility down to the queue pair level. And that is resulting in inability to identify root cause of issues quickly and resolve them in a timely manner. And this can happen, for example, during GPU cluster onboarding or UAT testing for the GPU cluster at the network level, at the fleet level, or it can happen for the AI workloads at runtime. At Clockwork, our foundational research is out of Stanford University. It is software-based clock synchronization. It is high precision at scale, provides sub-microsecond accuracy, and it measures one-way delays highly accurately. It relies on a probe mesh. So here, my first demo is on Oracle Cloud. I have 4 nodes here, and 2 of these nodes is in one rack, 2 of these nodes is in another rack. Each node has 8 GPUs and 16 network cards. The network cards are marked healthy as identified as detected by this probe mesh. And here is the probe mesh. So if I look at the one-way delays within the same rack between these network cards that have their clocks synchronized, I see around 600 nanosecond for each and every queue pair. And there's 4 over there, 4 queue pairs. Now, if you look at the one-way delays across 2 racks, then you see about 1.5 microsecond one-way delays. And right now, I don't have any workloads running, so this is just the network level visibility, fleet level visibility. And I'm going to kick off a job, an all-reduced job. That's just a standard job. It just got kicked off now between nodes 4 and 6. So I should be able to see nodes 4 and 6 throughput shoot up in a second. Here it is. So nodes 4 and 6 are getting 1.4 terabits per second. And that is the workload throughput that we're getting. And if I look at each and every one of these network cards, 32 of them, 91 to 92 gigabits per second is what I'm getting. Each network card is 100 gigabits per second network card. So that's pretty good. I'm close to max throughput. And if I look at the one-way delays before without the workload 1.8 and with the workload 3.2 microsecond is what I'm getting. So that is the type of visibility that is not there for GPU cloud operators and AI workload owners right now. They're not able to see the queue pair level visibility. The next is lack of reliability, and here's an alert. The link flapped over 10 times within the past hour, and you need to send technicians to swap out cables to fix this issue. This is fairly common in large enough clusters because you have large enough number of optical transceivers and they tend to overheat or dust particles affect them. So these network cards and links, they flap for just a few seconds, and that's just enough for the jobs to crash, which then forces the teams to restart from a previous checkpoint. And at best, teams are taking checkpoints every 30 minutes because checkpointing is also costly. And in addition, they're losing time and money for the duration of this downtime. So links can flap anywhere from top over X switch to spine layer switch at an interior link, or they can flap at the node to the top over X switch, so at the edge. And if it's a rail optimized design, then this last one is more critical because that node is losing its connectivity to the rest of the nodes on that rail. So here I have already a workload running. It's the all reduced job that's running between nodes 4 and 6. I'm going to flap a single NIC out of the 16 just to simulate this issue. And right now I can see that the job got grayed out and the job throughput went all the way down. So the job actually crashed. And the network card is now detected as unhealthy as well, so I know that it is down. Now, if you look at all of the network card throughputs, we have 16 other network cards there, but there's no workload on any of these network cards. Just because one flapped, the whole workload crashed. And if I bring back the network card right now, if I revive it, we will see that in a second it will come back. And you're seeing the network card is now marked as healthy by the probe mesh, but I can see that the job hasn't come back. So the job remains dead. And this is the point where I would have to fall back to a previous checkpoint and load all my training data, all my weights into the GPUs and start my job over if I have taken a checkpoint. Now, if you look at the one-way delays for this network card that flapped, I know it's healthy because probe traffic is back. I can actually see all the probes per second on each of these Q pairs, and I see the duration for which this card actually was out. So I know for sure the card is back, but the job has not come back. The job is still gray and throughput is down. So here I have on Oracle Cloud 3 runs, and the first run is just no failure. And I have 16 network cards, 100 gigabits per second each. Max I can get is 1.5 terabits per second, which is what I'm getting in this first run without any failures. In the second run, I simulated the same thing as the demo. So one NIC flaps and the job dies. You revive the NIC, the job doesn't come back. This is what's happening in GPU clusters today. And the last is about a solution that rises to this challenge and provides auto recovery from NIC flapping to prevent this type of crashes. So what happens here is the NIC flaps, but the job continues to run. It has a slightly degraded throughput. That's because we lost one NIC out of the 16 in this case. So the remaining 15 NICs, they're doing double duty. And that's why we have slightly degraded throughput. But when the NIC that got flapped comes back, then we recover back to max throughput. So this gives us a choice. The choice is if we want to fix this NIC or not, if we want to continue in this degraded throughput level or not. And it actually then becomes a choice of maybe we can run until the next checkpoint in this way. So the job didn't crash. We continue to run till the next checkpoint, at which point we recover back the NIC, revive back the NIC, and then recover back to max throughput. So that way we minimize downtime. Now, the last challenge is lack of predictable performance, and this typically exhibits itself as the application being slow. This is because the flows are contending for bandwidth. And when this happens, you see a degradation of throughput and high latencies. So here I have two senders, sender 1 and sender 6. And these senders are not aware which paths are more congested, which are less congested. So you see the light colored flows and dark colored flows indicating more or less congestion. And because the senders don't know which are more or less congested, so they're putting 50% of their data onto these paths. And you see on top at the spine layer flows, you see contention creeping up in the cluster. So here I have 3 runs again. and this is on an ECMP test bed. In the first run, all I have is an all-to-all job. And in this node, the max I can get is closer to 100 gigabits per second, but I'm only getting 84 gigabits per second. And the reason for that is actually in the graph below. The one-way delays for most queue pairs are around nanoseconds range, but for some of those queue pairs, we're at 50 microsecond range. And those slower flows are breaking down the job throughput so that it's not reaching closer to the max throughput it could get in this node. Now, if I introduce another job and another all-to-all job, now both of these jobs are actually getting 50% or less of what they could have gotten in this cluster, so 44 gigabits per second and 39 gigabits per second. The reason for that is in the graph below. The one-way delays for the queue pairs actually shot up for some of those flows, all the way up to 100 to 150 microseconds range. There's a lot of contention in this fabric. Now, this last run is about a solution that rises to this challenge, and it does congestion-aware load balancing. So it is shifting the bytes from more congested paths to less congested paths, which has the effect of reducing these one-way delays to the minimum they can get. So you don't have a large distribution for those one-way delays for the queue pairs, which then enables those two jobs to reach closer to their max throughput at 92 gigabits per second. So my key takeaways for you are fine-grained visibility into queue pairs accelerates identifying and resolving issues quickly when it comes to connectivity. For example, incorrect rail cabling is one of those issues. And this can otherwise take teams maybe days to resolve, but you could do this within minutes if you have fine-grained visibility down to the queue pair level. And this can happen not only during GPU cluster onboarding, but UAT testing for that GPU cluster before handing it to the AI workload owner, or it can happen for the workloads themselves at runtime. Nick and lick flapping. This is common in large enough clusters today, and it happens due to overheating and dust particles. So you want to checkpoint according to your business requirements so that you can recover from them without breaching any of your SLOs. Delays in your slowest queue pairs are going to reduce your overall job throughput, and this can happen by as much as 50%. So you want to monitor and optimize those slowest flows so that you can maximize your throughput. So a couple of hot takes for you. Just like intelligence built into the cars is more powerful than intelligence built into the track. When you're driving, when there's congestion on the road, you want that intelligence built into your cars. Measurement and control at the edge of the network is powerful, and it's going to supersede the network-centric approach. We believe in one unified circuit, many cars, and mixed parts. So we're going to have one network currently already carrying training and inference workloads. And this is because it's simply too expensive to be dividing your networks based on the function of your AI workloads. And soon we're also seeing storage workloads join in because of the benefits of RDMA. So the idea of designing these bespoke and partition networks for every AI workload, every type of AI workload, it's becoming obsolete. And the future is in unified AI networks. Finally, what's ahead? The AI network landscape is shifting. And past few years, we've been prioritizing speed and scale for our GPU clusters, but now we are more concerned with efficiency as our top priority. And just as computing evolved from monolithic mainframes to distributed systems, monolithic single vendor stacks, they're going to give way to heterogeneous environments with multi-generation GPUs and mixed speed network. So within this context that's constantly evolving, we believe a software-centric approach is going to adapt faster when it comes to delivering visibility, reliability, and performance for our AI workloads across this dynamic and complex landscape. Thank you.